Multiplication models and algorithms. So reminder, a a model explains why we do something the way we do it. And an algorithm shows us how to do it, how to get it done. So first we're going to take a look at the why, and we'll see how the why leads to the how, and we'll play with some base 10 blocks. So what the why basically gets down to, what does it mean to be multiplication? Right? Y is 2 times 3 equal to 6. And there's a few common ways that we think about that. One way is the idea of groups. So I can interpret this 2 times 3 as 2 groups of 3. And if I draw that, I have one group of 3 here. I have another group of 3 there, and I can see that there's 6 in there. So if I say, hey, multiplication just means groups of, 2 times 3 means 2 groups of 3, we can say, oh, okay, I see, it's 6. That's why it's 6. Another common way to think about multiplication is repeated addition. So with repeated addition, sometimes we look at this and we view it, if I do the 2 groups of 3 idea, if I continue that for the repeated addition, then I have a group of 3 and I have another group of 3. 3 plus 3 is equal to 6. If I wanted to look at the other way, like 3 times 2, that would be 3 groups of 2, which is going to look different, right? Here's a group of 2, here's another group of 2, and here's another group of 2. So is 2 times 3 the same as 3 times 2? The answer is, well, no and yes. So 3 groups of 2 is definitely different than 2 groups of 3. Like think about sports teams, like we're doing a little 3-on-3 basketball. That's different than 3 groups of 2. Okay, so physically, 3 groups of 2 is different than 2 groups of 3. The addition version of this would be 2 plus 2 plus 2, which is a different addition problem than 3 plus 3. But the result is still 6, right? And that result is called the product. So this idea of what we say is it doesn't matter what order you multiply in because you get the same product. Yeah, that's true. That makes multiplication commutative, but physically the order does matter even though the product's the same. So in my opinion, the most popular and useful versions of multiplication are this groups of here. So that's one model. And then the repeated addition is another model. So it's a physical explanation of what the heck does it mean to multiply. There's a few other models for multiplication. So those are the most popular. Other multiplication models. This one's probably my favorite, the area model. And the area model deals with rectangles. And so 2 times 3 would be, say, a height of 3 and a base of 2. So 2 times, oops, I drew that too tall. Fix that, 3. And I think of area as base times height. Some people think about it as length times width. That's okay too. And so here I have a base of 2 and a height of 3 in my picture. And then when I look at my picture, thinking about area, I see 6 squares in there. And that's kind of like this picture over here. But in this picture here, my groups of picture, those could be people or coins. That's a little bit different than an area, which an area I think about like something I would paint. Right? So I could paint that. Use my highlighter to paint it. And so if this was square feet, I would have 6 square feet to paint, right? So that's the area model for multiplication. The way I drew the groups of is often called the array model. So similar but different. The array model. And an array is just a rectangular grouping of things. And really, it's just a picture of the groups of model. And whereas this one is connected, continuous, this one is kind of like disconnected. So 2 times 3 again with the array, I would have, say, 2 rows of 3 things. There's 1 row of 3 things. There's the other row of 3 things, and they're set up in this rectangular array here. Right? So that's the array model. And the difference between these two kinds of models, this kind of model is called a discrete model. Discrete, oops. And it's discrete because it's made up of individual objects. And this model up here, the array, is called a continuous model. And it's continuous, kind of like paint, right? When I think about paint, it's hard to pick out an individual piece of paint, right? Because it's this liquidy thing that covers stuff continuously. Can't really see through it. So continuous is kind of like paint, and discrete is like individuals, individual coins, individual people, and we can group those people in a rectangular setting, like kind of at a table settings. And the other model is called the Cartesian model for multiplication. And the Cartesian model is kind of about choices, is the way I think about it. So perhaps I want to buy a car, and the car has 2 choices for the type of wheels. So 2 types of wheels. Right? I can either get the basic ones, or I can get these fancy rims on the car. And then I have 3 choices for color for this car, right? I could get a red car, or a blue car, or a white car. And if I can make a grid with these choices and maybe put the wheel choices over here and the color choices over here, my red, blue, or white, and my basic or fancy wheels here. And that gives me these different combinations in a grid here. Right, so I could get the basic wheels with a white car. I could get the basic wheels with let's do BL for blue. With a blue car, I could get the basic wheels with a red car. I could get the fancy wheels on a white car, fancy wheels on a blue car, or fancy wheels on a red car, and I get 6 total choices with the Cartesian model there. So it's just about organizing information, one thing after the other, and often when it's called Cartesian, it's put together in a grid like that. But we could make a tree to talk about it too. So that would be another way to do it. Backing up just a little bit. Array model is pretty important. Let me give that one a star. And the groups of model is pretty important. Sometimes that's called the set model for multiplication. It's the same as the groups of here, and then the repeated addition model. And they're all related because they're all multiplication. They all give the same answer, but they're just physical ways to state why should this be the answer when we multiply 2 numbers. So this is the why. Next thing we need to look at is the how to do it. So as far as the how goes, there's a couple things that we got to do there for algorithms. The first part really is basic facts. Like when I was in school, I had to memorize a multiplication table. And so I remember on my desk, there was this little card, and the card was labeled with a multiplication there. And then it went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And it's the same thing down this way. And although it's useful to know like 11s and 12s, it's not super important. Just kind of want to break down this multiplication table. That's kind of standard in our schools. So I have this 12 by 12 grid. So at first glance, 12 times 12 is 144. There seem to be 144 facts to know here. Turns out, no, there's not really 144 facts. So I'm just going to fill out a little about it. Multiplying by 1, well, that's kind of like boring, right? 1, 2, we get to, nothing happens. 3, 4, 5. So really, I think we can just kind of strike that row. Multiplying by 1 doesn't count. All right, so now I'm down to 11 by 11. That's better, 121 options. So multiplying by 2, well, kids learn doubles pretty young. So 2 times 2 is 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and so on. Multiplication by 3, that's important too, right? So 3 times 2 is 6. And then we have what, 9, 12, 15, 18, 21, 24, 27, 30, 33, and 36. Let's do a few more. We're not going to do all of them right now. 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48. And the 5s, 10, 15, 20, 25, 30, 35. Okay, this is getting boring. Let's stop there. Now, just something to note here, the 2s head out to the right, but they also head down here. And if you think about that, then I have this repetition coming down this way related to what's going across that way. So what we can think about on the table then is this diagonal that comes down with these perfect squares here. Trying hard to draw my diagonal. There we go. And what's above the diagonal is a match of what's below. So really, do I really need that stuff if it's already repeated above? But the answer is no, right? I know 6 times 3 and 3 times 6 is the same thing. So 3 times 6 is up here and 6 times 3 is down here. We don't need both of them, right? I don't need this number and that number because they're the same thing. All right, so we're knocking things out of here. Other thing, multiplying by 10 is super easy. We just put a 0 on it. Does that even count? Yeah, I guess so. And then really, I only need to memorize single digits because we have algorithms for double digits. So I really don't need the 11 and the 12. We could skip those. We don't have to have them because we have a procedure that's a process that doesn't involve memorization. So we're substantially cutting down the number of things that has to be memorized here. So it's not that bad. And so kids that struggle with this, right, we can help them narrow it down to some more important facts and other stuff they just don't have to worry about too much. So, but if you don't know some of those basic facts, then doing bigger problems is a problem. Okay, so we got some basic facts to do a multiplication table, and there's really nothing wrong with having kids use a multiplication table to do stuff, right? They have it sitting next to this to look at once in a while. The more they look at it, the more they'll remember stuff. That's okay. Calculators are good too, but we do need to know how to do some processes. Otherwise, it's going to be hard to move on to some other areas of study. So part of algorithms is basic facts, and the other is the process that we use. So a couple of processes, algorithms. So we have a carrying algorithm, but there are other ones. So let's take, for example, how about 23 times 36. Now, before kids get to double digits, they've done a ton of things like 8 times 7 is 56, and they're used to doing that. And so some kids, when they first get to this, are going to do things like 3 times 6 is 18. Right? We want them to put the 1 up there, and they can remember doing that from addition, but then they're going to have to carry stuff from these other rows, and that gets kind of tricky. So the first algorithm I'm going to show you is not this one you're probably used to, but what's called the expanded algorithm. In the expanded algorithm, you just need to recognize place value. So 3 times 6 is 18, no problem. And then this isn't really 6 times 2, it's 6 times 20. I know 6 times 2 is 12, so 6 times 20 should be 120. 3 times 3 would be 9, but this is really 30 times 3, so that's going to be 90. And then, although we might say this looks like 2 times 3 or 3 times 2, it's really 30 times 20. So I'm going to get a 6 with 2 zeros, so 600 for that one. And then we reconcile this, 8, 9, 10, 11, 12, 6, 7, 8. And again, that's what's known as the expanded algorithm. Cool thing about the expanded algorithm is it's related to the way we work with base 10 blocks. And so what I'm going to do is I'm going to turn this expanded algorithm into an area with base 10 blocks. And I think I'm going to get rid of the grid for this. Yeah, let's get rid of it. So the area means I have a base times a height. And when I draw my areas, I usually choose the bigger number to be the base. So I draw my picture out longer than tall, but it doesn't really matter. So I'm going to say my base is 36 and my height is 23. And I'm going to think about that with base 10 blocks. So I'm going to start off, say, here's my base down here, and here's my height there. And then I need to mark off what 23 and 36 look like here. So for color, let's see, if that's all I have to work with, then let's call that 10 right there. And another 10 would be about here. And then 1, 2, 3. So this would be my 23 there. And then if that's 10 that way, 10 over here would be about there. So 10, 20, 30, about there. 1, 2, 3, 4, 5, 6. So that would be my 36. So my area looks like this. All right. How does this relate to base 10 blocks? Well, if I built this with base 10 blocks, this 10 would go all the way up, and this 10 would go all the way up, and this 10 would go all the way up, and then so would my 1s. And it's usually easier to use real base 10 blocks, but it's good to learn to draw these. And similarly, going this way, I have my 10s going across, and I have my 1s going across. Okay, so not the best grid, not perfect squares, but close enough to my artistic stuff. All right, so when I do that, I see 4 distinct regions here. So I'm going to highlight them. I see this region right here. That's a bunch of 10 by 10 blocks. And let's use, say, yellow. I see this region, oops, yellow right here, which is a bunch of 1 by 10 blocks horizontal. And I have my 1 by 10 blocks vertical over here, right? Thinking about those base 10 block toys we have. And then finally, I've got, oops, the highlighter still, I've got this group of 1 by 1 blocks right there. And so in here, I see the following. I'm going to switch to blue. I see 1, 2, 3, 4, 5, 6 10 by 10 blocks, right? So I see 600 right there, right? This 600 right there. Over here, I have a 3 by 3 groups of 10s here. And so that's going to give me 9 10s or 90 right there. Over here, I have a 6 by 2 group of 10s. So that's 12 10s or 120 right there. And then here I have a 3 by 6 region of singles, which is just my 18. So the base 10 blocks in an area show me the expanded algorithm. And so we'll use that to build our standard algorithm next time.